The traveling salesman problem is an NP-complete problem, which means it can be solved in non-deterministic polynomial time. However, to find a solution in polynomial time, you can use heuristic algorithms. Heuristic algorithms can give you an estimated solution in a quick amount of time, although it may not be the optimal solution. One type of constructive heuristic algorithm used to find a short path for the TSP problem is the nearest neighbor algorithm. This is a greedy algorithm and it's efficient in finding a short path, but it may not be the optimal one. For this algorithm, you start at any vertex or city and you pick the nearest neighbor node to this city that has not been visited. You then mark this new node as visited and repeat the process again starting with the new node. To make this algorithm more effective, you can execute it multiple times, each time making the start node a different city. Then, when you have used all the cities at least once as a start node, you can pick the path that has the least total weight. A more accurate algorithm that can be used to solve the TSP problem is the genetic algorithm. Genetic algorithms are based on the idea of natural selection and evolution. A genetic algorithm consists of several steps: initialization, evaluation, selection, crossover, and mutation. In the first step, a population of any size is created. In the second step, the fitness of each individual is evaluated, and its fitness is based on how well it fits the requirement to solve the problem. In the selection step, individuals are chosen to mate based on their fitness level. What you can use is a weighted roulette wheel to choose which individuals will be chosen to mate. In this type of wheel, the individuals with higher fitness are given more portion of the wheel, but it is still chosen at random. In the crossover steps, new individuals are created by the chosen parents. And the next step is mutation, which adds variability into the new generation. Individuals are chosen at random to be mutated and at random mutation points. At the end of these steps, the entire process is repeated again, except for initialization. Neural network algorithms can also be used to solve TSP. Neural network algorithms are based on animals' central nervous systems and mimic some of their abilities. Examples of these models are the Cohonen self-organizing network and hot-field nets. In Cohonen neural networks, there are layers of neurons. One layer is the input layer, and the other layer is the output layer, and this is a grid network of neurons. Each neuron in the input layer is connected to every neuron in the second layer. The input, xy, is a coordinate of cities, and this input is put into the input layer. Then, the Euclidean distance is calculated between the input and output nodes. The node with the smallest distance is found, and its weight as well as the weight of its neighboring nodes are updated to be closer to the input. This process continues to repeat, and the neighbor radius decreases. The result is that the network will learn, and the states of the neurons will come equal to the coordinate of the input cities. The learning aspect of this algorithm is what makes it similar to animals' central nervous systems. The other neural network is hot-field nets. This consists of one dynamic weighted network. There are binary threshold nodes that act as both input and output, and the net acts to minimize an energy function. Input is given to a node, and from this, the net then calculates the output and iterates through updates until it is in a stable state. It achieves a stable state by using a weight update function and the energy function. The connection weights are adjusted as the energy function is minimized, which then results in a path solution. Those are just several examples of heuristic algorithms that can help solve the TSP problem in polynomial time. However, it may not find the most optimal and accurate solution.